In question 9, Ava is looking at different ways to tile a region with shapes. We're considering two options: tiling with squares and tiling with regular hexagons. We're told that a square tile and a hexagonal tile each have an area of 140 centimeters squared. The first task is to work out the length of the side of the square tile, correct to 1 decimal place. Well, there's a well-known fact about squares which says that a square with a side length of L will have an area of L squared. We're told that the area is 140, so we can set L squared equal to 140. To solve for L, all we have to do is take the square root of both sides. We can use our calculator to compute the square root of 140. And when we round to 1 decimal place, we get our final answer that the length is 11.8 centimeters. In the next part of the question, we must find the side length of one of our hexagonal tiles. This is a bit trickier. Thankfully, we've been provided with a diagram with some helpful labels. In this diagram, the hexagon is split into 6 equal triangles. One of these triangles has 3 labels written in: a 60-degree angle and 2 sides marked as X. Since the hexagon contains 6 equal triangles, we can deduce that the area of the hexagon will be 6 times the area of one of these triangles. We know that the area of the hexagon is 140, so if we can write the area of a triangle in terms of X, we'll be able to use this equation to solve for X. To find the area of the triangle, we can use a result from page 16 of the formula book. It says that the area of a triangle is equal to 1/2 times A times B times sine C. Here, A and B refer to the lengths of 2 sides of the triangle, and C refers to the angle between these 2 sides. In the label diagram we've been given, we have 2 sides and the angle in between. To use our formula, we can let A be equal to X, B be equal to X, and C be equal to 60 degrees. Subbing these in gives us 1/2 times X times sine 60. X by X simplifies to X squared, and using our calculator, sine 60 becomes √3/2. To simplify further, we can multiply the 1/2 by the √3/2, and this gives us √3/4 times X squared. Now that we have an expression for the area of the triangle, we can write it into the equation we had and then solve for X. In our equation, the X squared is being multiplied by a constant, 6 times the square root of 3/4. To remove this multiplication, we should divide both sides by this number. We now know what X squared is equal to, so to solve for X, all we have to do is remove this square. We do this by taking the square root of both sides. We can use our calculator to compute the expression on the right-hand side. It comes out as 7.340710. We were told to round our answer to 1 decimal place, so the final answer here is that X is equal to 7.3 centimetres. In part B, Ava is considering a more complicated tile. Here, each tile consists of two parts. An arrowhead, A, B, E, D, which I've coloured in blue, and a quadrilateral, E, B, C, D, which I've coloured in red. In part I, we're provided with several side lengths. We're told that AD is equal to 8 centimetres, AE is equal to 6 centimetres, and ED is equal to 4 centimetres. In the diagram, one of the angles is labelled alpha, and we must show that alpha is equal to cosine inverse of 7/8. Well, if we take a look at the values we're given, they all live in the same triangle, AED. Let's focus in on this triangle. We know all three side lengths, and we're trying to find an angle. So all in all, we're working with 3 sides and 1 angle. This is precisely the setup we need to use the cosine rule. This says that a squared is equal to b squared plus c squared minus 2bc times the cosine of capital A. Here, capital A refers to an angle, and in our diagram that will be the alpha. Lowercase a is the side opposite this angle, and here A will be 4. B and C refer to the other 2 side lengths. Here we can let B be equal to 8 centimetres and C be equal to 6 centimetres. Let's sub these values into our formula. From here we can simplify a bit. 4 squared is equal to 16. 8 squared plus 6 squared comes out as 100. And minus 2 times 8 times 6 is equal to minus 96. The result we need to show has alpha all by itself on one side of the equation. So the target here will be to isolate the alpha. To start, we can get rid of the plus 100 by subtracting 100 from both sides. From here, we can simplify on the left. 16 minus 100 is minus 84. Next, we can get rid of the multiplication of minus 96 by dividing both sides by minus 96. Now, if we use our calculator to simplify the fraction on the left-hand side, it comes out as 7/8. Finally, to get rid of the cos, we need to take cos inverse of both sides. This tells us that alpha is equal to cos inverse of 7/8. This is precisely the result we needed to show. In part 2, we're told that the angles ADC and ABC are equal to 90 degrees. We must use this to work out the total area of the quadrilateral ABCD. A good place to start here is to focus in on the triangle ADC. This triangle makes up half of our quadrilateral, so if we can find the area of this triangle, we can simply double it to find the area of the quadrilateral. Well, we're told that the angle ADC is 90 degrees. In other words, it's a right angle. So we can use the results for sine, cos and tan in right angle triangles. we're trying to find the length of AC, and that corresponds to the hypotenuse in this triangle. Focusing on the known angle, alpha, the side AD, which is 8 centimeters, corresponds to the adjacent. Since we're working with the adjacent and the hypotenuse, we can use the result that cosine of alpha will be equal to the adjacent over the hypotenuse. In the previous part of the question, we found that alpha is equal to cosine inverse of 7 over 8. We've shown that the adjacent is 8 and that the hypotenuse is the side AC. Some nice cancellation happens on the left. The cosine will cancel the cosine inverse, so we're left with 7 over 8. Next, we can multiply both sides by the side length AC. And finally, we can divide both sides by 7 over 8. When we calculate 8 divided by 7 over 8 in our calculator, we get 64 over 7. Now that we know the length of AC, we have two side lengths and the angle in between. So we're ready to use our formula for the area of a triangle. A half times A times B times sine C. Here, we can let A be equal to the side length AC, which is 64 over 7. Set B equal to the side length AD, which is 8. And set C equal to the angle in between these sides, alpha. In the previous part of the question, we found that alpha is equal to cosine inverse of 7 over 8. Typing this big expression into our calculator will give us the area. It's 17.7051. We were asked to find the total area of the quadrilateral ABCD. But as we mentioned earlier, this shape is split evenly into two halves, an upper triangle, ADC, and a lower triangle, ABC. We've just found that the area of the upper triangle was 17.7051, and by symmetry, the area of the lower triangle will be the exact same. To find the total area of the quadrilateral, all we do is add the area of these two triangles. When we perform the calculation and round to 2 decimal places, we come to a final answer of 35.41 centimeters squared. In part C, Ava is looking at tilings of the unit circle. We are provided with a diagram of the unit circle, and there's been 3 points labelled: O, P, and Q. We are told that the angle QOP is 45 degrees. To help visualise this, we should draw in the side QO. Something worth noting here is that QO is a radius of our circle. Since we're working with the unit circle, which has a radius of 1, we know that QO will have a length of 1. In the question, we are asked to show that the point Q has coordinates minus 1 over root 2, comma 1 over root 2. Well, the coordinates of a point correspond to the movements needed in the x and y axis to get from the origin to that point. We can visualize these movements if we drop a vertical line directly down from Q so that it meets the x-axis at a right angle. The horizontal x movement corresponds to this side length, and the vertical y movement corresponds to this side length. If we focus in on this right-angled triangle, we can use some trigonometry to find these side lengths. Focusing on the 45-degree angle, the sides in a right-angled triangle can be labelled with adjacent, opposite and hypotenuse. The hypotenuse is the side opposite the right angle, which here is 1. The opposite is across from the 45-degree angle, and here that's y. The adjacent is the third side, and here that's x. In a right-angled triangle, the cosine of an angle is equal to the adjacent over the hypotenuse. Here, the angle is 45, the adjacent is x, and the hypotenuse is 1. If we type cosine of 45 into our calculator, we'll get 1 over root 2. The right-hand side, x divided by 1, simply simplifies to x. So we found that x is equal to 1 over root 2. We can find y in a similar way if we apply the result that the sine of an angle is equal to the opposite over the hypotenuse. In our triangle, the angle is 45, the opposite is y, and the hypotenuse is 1. If we calculate sine 45, we'll get 1 over root 2, and if we simplify the right-hand side, we can see that y over 1 is just equal to y. So we found that y is also equal to 1 over root 2. Now let's put everything together to get the coordinates of Q. We've shown that Q is located 1 over root 2 units to the left of 0. Since movement to the left corresponds to negative x values, we can conclude that its x-coordinate is minus 1 over root 2. We've also shown that Q is located 1 over root 2 units above 0. When we move upwards, it corresponds to a positive y value, so we can conclude that the y-coordinate is plus 1 over root 2. In the final part of the question, we're told that P lies on the x-axis. We're then told that the centre of our circle lies at the intersection point of two lines, the tangent line at the point P and the tangent line at the point Q. I've drawn in these tangent lines in our diagram. The tangent line at P is drawn in purple, and the tangent line at Q is drawn in pink. In the question, we've been asked to find the centre and the radius of the circle S. Well, we've been told that the centre occurs at the intersection point of the two tangent lines. The strategy here will be to find the equation of both tangent lines, and then use simultaneous equations to find the intersection point. To begin, let's focus on the tangent line at P. The first thing to think about is the coordinates of P. Since we're told P lies on the x-axis, it must have a y-coordinate of 0. Since P lies on the unit circle, which has a radius of 1, we can deduce that the x-coordinate is minus 1. To find the equation of the tangent line, we'll need to use a useful fact. The tangent line to a circle at a given point is perpendicular to the line joining that point to the centre of the circle. So, if we join our centre, O, to the point P, the tangent line will be perpendicular to this. Since the line OP is completely horizontal, a perpendicular line will be completely vertical. This means that the tangent line at P will be the vertical line which is drawn at an x value of -1. In other words, the tangent line will have the equation x is equal to -1. Now, let's turn our attention to the tangent line at Q. To find the equation of a line, there's two things we need to know: a point on the line and the slope of the line. We already know a point on this line, it's Q. And in the previous part of the question, we found the coordinates of Q. However, we don't know the slope. To find this, we can use the fact that I've written. The tangent line at Q will be perpendicular to the line which joins Q to the centre, O. The strategy here will be to first find the slope of this blue line, OQ, and then use this to find the slope of the pink line. Well, given 2 points on a line, we can find the slope of the line using the formula y2 minus y1 over x2 minus x1. As it turns out, we know the coordinates of 2 points on the line OQ, namely O and Q. O is the centre of the circle, which has coordinates 0, 0, and we label these with x1, y1. Q has coordinates -1 over root 2, 1 over root 2, and we label these as x2, y2. These coordinates were provided to us in the previous part of the question. If we sub these values into our slope formula and perform the resulting calculation, we end up with -1. So the slope of the blue line, OQ, is -1. The pink line is perpendicular to this, and there's a trick we can use to find a perpendicular slope. We flip the fraction and change the sign. To do this, it would be wise to first express our slope as a fraction. So I'll rewrite -1 as -1 over 1. Using this trick, we can flip the fraction, which actually just gives us back 1 over 1, and we change the sign from a minus to a plus. This tells us that the slope of the pink line, which is the tangent at Q, is +1 over 1, which simplifies to 1. We're now ready to find the equation of the tangent line at Q. To do this, we'll use the formula y minus y1 is equal to m times x minus x1. Here, m is the slope, and we found that the slope of this line is 1. The x1 and y1 refer to a point on the line, and here we can use the point Q. This has an x-coordinate of -1 over root 2 and a y-coordinate of 1 over root 2. Let's go ahead and simplify a bit. -1 over root 2 is the same thing as +1 over root 2. The subtraction of 1 over root 2 on the left-hand side can be removed by adding 1 over root 2 to both sides. 1 over root 2 plus 1 over root 2 simplifies to root 2. Now we've got our equation in a nice format. Y is equal to x plus the square root of 2. Remember, we were told that the centre of S was the intersection of the two tangent lines, the tangent at P and the tangent at Q. We've now found the equation of each of these lines. The equation of the tangent at P was x is equal to -1, and the equation of the tangent at Q was y is equal to x plus square root of 2. We can solve these simultaneous equations to give us the coordinates of the centre. And as it turns out, these are a very easy pair of simultaneous equations to solve. That's because the first equation gives us the x value directly. It literally says that x is equal to -1. To find the y value, all we have to do is sub in x equals -1 into our second equation. When we do this, we see that y is equal to -1 plus the square root of 2. Writing our x and y value together in a pair tells us that the coordinates of the centre are -1, -1 plus root 2. We were also asked to find the radius, but thankfully this is quite straightforward. Since we're told that P is a point on our circle, the radius will be equal to the distance from the centre, -1, -1 plus root 2, to P, -1, 0. Since these 2 points have the same x coordinate, -1, the distance between the points will simply be the difference in the y coordinate. Well, the y coordinates are -1 plus root 2 and 0, and the difference between these two values is simply -1 plus root 2. So that'll be the radius of our circle.